All right, so yesterday we started talking about resonance, and we said when we look at Lewis structures, sometimes they're not super accurate representations of molecules. So we looked at an example where the bond length wasn't alternating between a double and single bond. Experimentally, we knew that those bonds were the same length and that the negative charge was shared across multiple atoms. And then we looked at the orbital reasons why. And in these examples, we said whenever you have these aligned p orbitals, you can share electron density between, in this case, a pi bond and a positive on an sp2 hybridized carbon. And then we got into this weird example down here where we said Vesper theory predicts that the carbon on the right would be sp3, but if it were sp3, we couldn't move that negative charge around. It would be stuck on that right carbon. However, if it were to adopt an sp2 hybridization, then we can delocalize, and that is experimentally observed. So what we're going to do today is practice drawing resonance structures. We did a little bit yesterday, but didn't get too far into it. And I'll show you my basic rules. The first rule that's super, super, super important whenever you're doing resonance structures is never break sigma bonds. We saw in the previous examples we could move lone pairs and we can move pi bonds, but we never ever broke a sigma bond. That is to say, we never break single bonds, right? All right. Second rule is never exceed an octet. Of electrons. What do we call that on a carbon? Texas carbon. We never want to see Texas carbons. Third one is kind of related to number one. It says only move pi bonds or lone pairs. You never want to move anything else. All right. And then number four involves the arrow pushing. We're going to use arrows to show movement of electrons. You don't use arrows to show movements of positive charge. It seems kind of counterintuitive, but always show arrows whenever you move electrons. So in this case, you're going to have an electron source, and in this case, it's going to be a pi bond or lone pair. And you're going to show an arrow going to the electron destination. And it is pretty important to remember for your electron destination, you cannot exceed an octet. And your electron destination is going to be either sp or sp2 hybridized. It has to have a p orbital, right? All right, so let's take a look at some examples. And the first one's kind of silly, but bear with me. I think it does a good job of explaining what's going on. Whenever we have a resonance structure, we use brackets, right? And in this case, we're going to have a blue horse on one side, and it's in resonance with a red donkey. Yeah, how many electrons does a red donkey have? I have no idea. If we think about the hybrid structure, what would be a better hybrid structure for this? I'm kind of giving it a hint. Purple mule, exactly. So the thing that confuses organic chemistry students is they think it's constantly flip-flopping back and forth between a blue horse and a red donkey. That's not the case. That's just the way we choose to show it as chemists. The reality is a more accurate descriptor would be it's a hybrid of both of those resonance structures, so it would be a purple mule. So when we practice resonance structures for the first few weeks, I'm going to ask you to draw hybrid structures to really drive home the point that it's not flip-flopping, it's a hybrid of both resonance structures, or if there's more than two, it's going to be a hybrid of all of them. Okay, so let's practice again. All right, the first one we saw yesterday, it was this allyl cation. I'm not going to show all of the hydrogens because we've got bond line notation, right? And in this case, we always want our arrow to start at lone pairs or pi bonds, right? So over here we can say, well, we've got a pi bond. We're going to move that pi bond over here. And whenever you draw resonance structures, you're not creating or destroying charge. So your resonance structures need to have the same net formal charge as the structure you started with, right? So these would be the two valid resonance structures. And students get confused and they say, well, aren't these the same? Kind of, right? They look like mirror images of one another. But we have to show both of them to show that positive charge is being shared between the right carbon and the left carbon. So we need to show both of them. And in this case, our hybrid view, like we saw yesterday, is going to be a partial double bond going between all three of those carbons. And the left carbon is sharing a positive charge along with the right carbon, so you can show it that way. So this would be a more accurate hybrid view. Yeah?
What does the three-line mean?
Oh, that just means equivalent to. Yeah, good question. So this just means equivalent to. That's my shorthand. Some math teachers use it. Whatever you want to do, you can. Yep. Let me just write hybrid here. All right. So let's do the next one that we covered yesterday. This one we had a negative charge. We need a double-headed arrow. Never ever show it with a single-headed arrow. What does a single-headed arrow represent? It means a reaction, right? We're not reacting anything. We're just showing that electrons can move around in this molecule. All right, so now the question is, how are we going to push these electron arrows? So let's try doing it this way first. If we do this, we would have a negative charge still right there. We would have a positive charge right there. Does that make sense? What's the problem? Well, let's think about this, right? I'm actually going to draw in my hydrogens here. I heard somebody say it. That's good. Students get tempted to draw it like this and say, well, I moved the pi bond. Isn't this okay? I would point to this carbon and I'd say this violates the octet rule. Nah, don't violate the octet rule. All right, so that's not a valid resonance structure. We've got to try something else. What can we do if we can't move the pi bond? Move the lone pair, exactly. So what we'll do is we'll say, all right, we're going to move this lone pair down over here. And then same thing, students will say, perfect. Oop, let me keep the colors the same. If I do that, now I have a double bond like this. Is that okay? No, because we have an assumed hydrogen right there, so now this carbon would have more than an octet. But we can fix that. If we want to make sure that that central carbon doesn't violate the octet rule, we can move this pi bond over to that carbon, right? So we can go ahead and say the structure should look like this with the negative charge all the way over there. We have only moved lone pairs and pi bonds. We haven't violated the octet rule, and we haven't broken or moved sigma bonds in any way. Okay, so now if we think about the hybrid, it looks pretty similar to the one on top. So I'll go ahead and show that as delocalized, but this time we're delocalizing a negative charge across the left and the right carbon. So really, really double check, make sure you're not violating the octet rule anytime you're doing arrow pushing. Does that make sense? All right, let's do another one. We'll go all the way back to the quiz. Dun, dun, dun. We have the nitrate anion. And I'm going to show all of the lone pairs. We've got some options here, right? So one option, oops, I'm forgetting my positive charge. One option would be to move the pi bond. We could do that if we want. So For example, I could kick this one up to the nitrogen. Why wouldn't I kick it down to the nitrogen? So let's just try that, right? So I could say, well, what happens if I move this pi bond down to the nitrogen? And people are tempted to because they say, well, that nitrogen has a positive charge. Wouldn't it want those electrons? But let's try, even though I'm forewarning you that it's wrong. So now this oxygen has a single bond to it. This is negative, this is negative, this is positive. What's the formal charge for that oxygen up there? Positive. And what's the other problem with it? It doesn't even have an octet. That just doesn't make a whole lot of sense, right? So in this case, we're probably not going to do that. Not only does oxygen, being an electronegative atom, really not want to be positive, it would much rather have an octet too. Yep. Oh, yeah, sorry. The nitrogen would be neutral in this case. You're entirely correct. All right, so let's do it the opposite way and say, all right, if that's not the case, what if we do the opposite and we pull this pi bond up? Now this oxygen can have a negative charge, but what's the problem there? The nitrogen doesn't have an octet. And what would the charge be on nitrogen? 2 plus. Never going to happen, right? Nitrogen's relatively electronegative, but we can fix this. All right, how can we fix that? Yeah, pull electrons from one of the oxygens that's negative. So for example, I could say, all right, I'm going to move this one down, and if I do that, one of these lone pairs is going to form a pi bond, and this nitrogen will have a positive charge. So now we haven't violated the octet rule, we haven't broken any sigma bonds, and the overall net charge is still -1 for each of these, right? Okay, now we can try this again, and we could say, all right, maybe I'm going to pull electrons up to this oxygen, and then I'm going to pull one of these lone pairs down. Okay, so now we've got a double bond here. We have 2 remaining lone pairs on this oxygen. We have a single bond to this oxygen with 3 lone pairs on it. And then this other one's just kind of staying put from the old structure. And the nitrogen has a positive charge. Are there any others that we can do? Well, let's try it, right? I could say, well, let's pull this down and kick electrons over. And if you do this, now you've got oxygens with negative charges on the bottom. What do you notice about this one? It's the exact same thing as the first one. So you could do this for years and years and years, but you don't need to draw them over again. Once is good enough for me. Yep.
So why are you, or does it matter? You're pulling the 2 electrons from the pi bond and putting them into the, or up to the oxygen. Could you just move the electrons from the pi bond to form another pi bond with the other oxygen instead of?
Yeah, so that's a good question. So let me see. I'm going to redraw these arrows. So you're just saying, why don't we do something like that? If you do that, then you have more than an octet on that or on the oxygen. So you do have to be pretty careful with how you do these. It's really easy to make those simple mistakes when you're first doing resonance structures. So I always say, if it helps you to draw all your hydrogens in lone pairs, absolutely do it. Okay, so these are all 3 that I can think of for nitrate. So we can now draw the hybrid view. And anytime you draw a hybrid view, I recommend just draw your sigma bond network first. And in this case, this has partial double bond character because we can see in this structure over here it has a double bond. And the same is true for all of the other oxygens. So we can draw it dashed like that. And all of the oxygens are sharing that negative charge. So I'll go ahead and draw partial negatives on this oxygen, and on that oxygen. Makes sense? Because when we look at all the resonance structures, the first one has a negative charge on that oxygen, but in the last one it doesn't. So it's not a permanent full negative charge on that left bottom carbon. It's only carrying that in some of the resonance structures. Yep?
So do you still have to draw the positive charge on the nitrogen?
Yes, absolutely. So I'll go ahead and say in all of these structures, though, nitrogen has a positive charge. So I'll plug that in and say it's not a partial positive, it's a permanent positive. It can't delocalize that positive charge anywhere. So this would be the hybrid view for nitrate. If we think about the partial negatives on the oxygen, and we tried to assign a numerical value to them, what would it be? It's not -1. It'd be -2/3, right? Because it's 2 negative charges shared across 3 atoms, right? So in this case, each oxygen technically has a -2/3 charge. It's a little bit weird. If we think about the bond order between nitrogen and oxygen for all of them, what will the bond order be? It's not single, so it's not 1. It's not double, so it's not 2. It'd be 1.33333333, right? So it's not a true single or a double bond. It's a hybrid. Technically, it's a bond and a third. Make sense? Yeah.
So for the weight, we'll ask about the weight side. So I saw that some people draw like a cardio line.
Yeah, some books might show a just regular solid curved line. I don't like doing that because that implies a double bond. I like the dashed line to indicate it's not a true double bond. It's kind of in between. Yep. All right, so let's take a look at some of these. And I'll give you a harder one. All right. And I'm going to draw out all of my hydrogens just so we can keep track of octet rule violations easier. And like I said, you're welcome to. Sometimes you'll see resonance structures where you're not moving charges around. And these are a little bit tricky. But the same exact rules apply, right? So you can move pi bonds and you can move lone pairs. Okay, so let's try. If we, let's say, move this lone pair, where can I move it to? Can I move it over to this bond? No, I can't. Why not? Yeah, we'd violate the octet rule on that oxygen. Okay, so what I can do next is I can say, well, if I can't move those electrons there, maybe I'll move them to that adjacent bond. Can I do that? Well, if I do that, then this carbon right here would have more than an octet of electrons, but we can fix that. I'm going to take the pi bond electrons and say, all right, you now belong to this carbon. The key thing to remember is you always are dealing with adjacent bonds or adjacent atoms. You can't go further than that when you're doing electron pushing. Okay, so now we've got a double bond between this nitrogen and carbon. We can't forget about formal charges, though. What's the formal charge on nitrogen? Positive. All right, and we've got a lone pair now on this carbon that was on that pi bond. So what charge will that carbon have? Negative. You notice how we didn't change the overall formal charge on either resonance structure? What do we call that when we have a positive and negative? The Zwitter ion. So in this case, the formal charge for the left molecule and the right molecule are both neutral. And you can do resonance, like I said, with neutral molecules. Which do you think is the more important contributor, the one on the left or the one on the right? Meaning, which form do you think the molecule is happiest being in? The one on the left, right? Molecules like minimizing charge. So while we can draw resonance structures like the one on the right, they're thought of as minor contributors, not major contributors, and we'll talk more about that in a few minutes. All right, now next question. What's the hybridization of the nitrogen? Check with your neighbor and see if you agree. All right, give me a thumbs up if you agree with your neighbor. All right, let's do an informal poll. Raise your hand if you think it's SP2. Raise your hand if you think it's SP3. Raise your hand if you're not sure, not voting. A few people. All right. Let's think about it this way. Can we delocalize the lone pair on nitrogen if it's SP3? No. In this case, even though the one on the left looks like it's SP3, like we saw yesterday, if you're able to move electrons past that atom, it has to have a p orbital, right? So in this case, it would have to be sp2. So it must be sp2 in order for delocalization to occur. So it is kind of confusing. Vesper theory, you always have to take with a grain of salt. Anytime you're assigning hybridization or bond angles, you have to say, is there resonance? If there's resonance, then you might have to assess whether or not the hybridization is what it appears to be. It is tricky that way. All right, so let's think about the hybrid view of this one. And I'm just going to go to bond line structure. We would say, all right, nitrogen has two methyl groups coming off of it. Sigma bond network should look like this, right? Now we'll include all of our electrons. And in this case, this nitrogen carbon bond is double bond like, right? Because in this structure over here, we've got a double bond. All right, but in this structure over here, we've got the double bond between the two carbons. So let's go ahead and add in that. So we can show that delocalization is occurring across all three atoms. And now we can also show the charges as well. And we could say, all right, this nitrogen's going to carry a partial positive on it. And then the carbon is going to have a partial negative on it. So this is a little bit harder hybrid view to draw because we're not having as much delocalization. Make sense? All right, let's do another one. Yep.
So is it partial positive and partial negative because the first one is neutral?
Yeah, so if we think about why it's partial positive and partial negative, the nitrogen on the left molecule is neutral, but on the right it's positive. That means the hybrid is somewhere in between neutral and positive, so partial positive. Great question. Yep.
So because it's more likely to be the one that taking the bond order.
That's a good question. It would be hard to predict the bond order for this molecule because we know that they're not equal contributors to the resonance structure. It's going to probably be much closer to the representation on the left, though. So the carbon-carbon bond is going to be pretty dang close to a double bond. Yep. Yep.
Question, more in regards to the previous example. Is there a way for us to look at the NO3 structure and know that there are two electrons that are being shared amongst the three oxygens, or is it just implied?
Yeah, so the question was about nitrate and how many electrons there are. First thing you always want to do is draw a valid Lewis structure. And in this case, then draw as many possible resonance structures as you can that don't repeat themselves, and then don't violate the octet rule, don't break sigma bonds, and so on. And then once you have all of those drawn, then assess the hybrid view. We saw in nitrate, we had three oxygens that were ultimately equally sharing two negative charges. So we said it would be negative 2/3 formal charge for each of these. Whenever you have structures like this, people will say, don't these look incredibly similar for nitrate? Absolutely they do. These are equal contributors, right? One doesn't look more stable than the other. In fact, they almost look like they're rotating. These are called degenerate contributors or equal contributors. So we will run into those on occasion. However, like we saw down here, sometimes we run into unequal contributors as well. All right, now I've got another one. For this other one, I want to ask the same question about nitrogen. So this time we've got it attached to a carbon. And the nitrogen has a lone pair. What's the hybridization of this nitrogen? All right. The main thing you would have to ask yourself is whether or not there's delocalization across that nitrogen. So I could say, all right, I can move pi bonds and I can move lone pairs. I don't have any pi bonds to move, but maybe I can move this down there. Can I do that? No. If I try to, you're going to end up with one of those Texas carbons that I hate. So you'll have that double bond here. Let me just finish drawing it out. I would put a big X through this, and I would say Texas carbon. All right, because we can't delocalize those electrons, that means that the nitrogen will be sp3 because it doesn't need to be sp2 to begin with. It would rather adopt a preferred geometry if possible. So in this case, this nitrogen is sp3 since there is no delocalization. It is tricky, but in order to predict hybridization, you have to know the possible resonance structures. All right, so like I said, not all resonance structures are equal. When we went up and we saw nitrate, we said they were equal, but with the one below it, the challenge problem, we said they weren't equal. So let's try to come up with some sort of system for predicting what's the most important resonance structure. And I've got a set of rules that are pretty simple to follow. So the first one is full octets take priority. You might have occasions where you have an atom with less than 8 electrons, but typically those are going to be minor contributors. They're not going to be the most important contributors. So I'll show you an example of this. The example is carbon monoxide. So CO. CO looks like this. It's that gas that you should have the gas that you should have a detector for in your home. Does anybody know why? Yeah, it reacts with red blood cells, and unlike CO2, if you inhale a lot of it, you'll feel it. Your muscles will start burning. You'll start feeling like you ran a mile. It's just a nasty feeling of lactic acid building up in your muscles. Carbon monoxide, on the other hand, can't smell, you won't feel, you'll just get sleepy, pass out, and die. So make sure you have a CO detector. All right, what's the formal charge on carbon? Minus? What about oxygen? Plus? All right, what we could do is we could say, well, couldn't we kick electrons over to that oxygen? So let's try that with resonance structures. So now we've got 2 lone pairs there. The lone pair on carbon hasn't changed. All right, what's the formal charge on carbon now? It's 0, it's neutral. What about oxygen? 0, it's neutral. Okay, so technically we could draw these as resonance structures. The formal charge hasn't changed. We haven't broken any of our resonance rules. All right, but if we think about octets being full, which molecule is happier, the one on the left or the right? The one on the left. The one on the left, even though it has charge, has full octets on both atoms, it's way happier. So I'll write major contributor. This one's minor because it does not have full octets. And it's something that throws people off because they say, well, the major contributor has a positive charge on oxygen. Oxygen's electronegative. How the heck does that work? And I'd say ignore charge. Octet takes priority over charge every single time. It seems counterintuitive from what you were taught in Gen Chem. All right, second one. If tied, the structure with minimized charge takes priority. All right, so I'll show you an example of this. Let's say I've got this compound. Let me do another one. We'll come back to that one. I'm trying to think of an example off the top of my head, and I can't right now. But the idea, I guess, let's actually go back. We already did an example. In our challenge problem, right? We said the structure on the left was a more important contributor because it didn't have charge, meaning minimized charge, compared to the one on the right that did. So this would be an example of the one on the left being a major contributor. All right, so that's pretty self-explanatory. Octets are number one. Number two is try to minimize charge. The one with minimized charge will be more important. Third one is if there's still a tie. So if still tied, then pay attention to electronegativity. And what I mean by that is the more electronegative atoms prefer to carry a negative charge if you're still tied at that point. All right? And then 4 is an important one. Avoid / don't draw structures with a carbon that's positive and a carbon that's negative. You don't typically want to show that, and I'll show you why. Let's say we have a simple alkene. Oops. This would be ethylene. Students will get tempted to say, hey, can't we just move this pi bond over to that carbon? If we do that, this carbon would now have a negative charge. It would still have both hydrogens on it. And the carbon on the left would have a positive charge. There's a few problems with this. Violates rule 1. We've now don't have octets, so that means the one on the right already isn't important to begin with. And then if we think about it, we know experimentally that there really isn't any partial negative charge on either of those carbons. And then conversely, you could say, well, why did you choose to push it that way and not that way? It just doesn't work very well, so don't bother breaking pi bonds between two carbons like this. Avoid drawing any structures where you have C positive and C negative. So super minor. Don't draw. All right, so I'll give you a practice problem, and I want you to come up with all of the resonance contributors and then label them from most important to least important. All right. And I'm going to draw out all of the atom labels as well. And there we go. So I'll give you a few minutes to do this. There are 2 additional structures that you can draw. All right, so let's try to do this as a class really quick. So if you remember, we can only move lone pairs and pi bonds. So I'm going to just pick the pi bond. You could start with the lone pair if you really wanted to. So for example, I could say, all right, this pi bond, will I want to move it down? Nope, why not? Octet rule, we can't do that. So instead, we would say, let's move that pi bond up to the oxygen. We'll have our double-headed resonance arrows. If we do that, what's the formal charge on the central carbon? Positive. Do we really need to draw this resonance structure? Yeah, I just went up here and I said don't draw resonance structures with C plus C minus, so I'm going to immediately label this one as super minor. Don't need to draw. In addition to having C plus C minus, what's the other thing going on? Yeah, the octet rule. That central carbon doesn't have an octet. So we don't need to draw this middle one. You can, while you're practicing, sometimes it helps just to see the movement of electrons. All right, next thing we can do is we can delocalize a lone pair. And you've got some options, right? Sometimes students will say, well, can I move this lone pair down? If we do that, we're just making what we had before, so we're running around in a circle. You're welcome to run around in a circle, you just won't get far. All right, alternatively, what you can do is take this lone pair and dump it down. Okay. Now we've got a double bond here, and we've got a single bond to the oxygen. All right. So really, there are two resonance structures I would expect you to draw for this one. The middle one, like I said, you don't really need to draw, but if you're practicing and it helps, you can. Yep.
Can we go directly from the first to the third because this will involve switch?
Yeah, exactly. So your question is, can't we go from the first to the third?
Yeah.
Absolutely. So you could go like this, have two arrows, and do this all in one step. Whoops. It would look like this, and then you would have your oxygen with the negative charge like that. So you could do it in one step if you would like. All right, so now my question is, we know the middle one is obviously the least important, so I'd say third. It violates rule 1, it violates rule 4, and it's got a heck of a lot of charges on it, which is what we're looking at in rule 2. All right, now between the first one and the last one, which was more important? Okay, so the last one, I heard people say that. Anybody want to share why? So rule 1, I would say, is satisfied in both of those, right? We've got full octets in our first structure and our last structure. And then we go to rule 2, and we'd say minimize charge. Well, they both have a negative charge. They're just on different atoms. So then we'd say, all right, if still tied, then pay attention to electronegativity. All right, so now let's look at it. Which one's going to be the major contributor? I would say the one on the right. Oxygen is far more electronegative than carbon. It's happy with the negative charge, or relatively happy, I should say. So this would be priority 1, priority 2, and priority 3. If we try to draw the hybrid structure, we don't even need to worry about 3. Instead, we can say, okay, 1 and 2 are the most important ones that we should care about. We'll draw our sigma bond network. Looks like this. We're delocalizing our charge across both of these. We're going to have a partial negative on oxygen that's pretty large. It's going to hog that electronegativity, so I'll make that delta symbol quite big. This carbon down here isn't very electronegative, so it's going to have a little delta minus. All right, which bond is going to be shorter, the carbon-carbon bond or the carbon-oxygen bond? Let's think about it, right? Our major contributor had a carbon-oxygen single bond. Single bonds are typically longer, right? So in this case, we would expect this bond to be a little shorter. So we'd say more double bond like than the CO bond. Does that make sense? It is kind of tricky, but use the list and try to follow the order. Like I said, it's not intuitive that octets are more important than charge, and that's the thing that tends to trick people up when they're working on these. All right, so tomorrow we'll do a bunch of practice. If you'd like to get started on your pod, you're more than welcome to. I'll let you work on it during class, though, and I'd like for everybody to help each other out with the practice problems as well. All right, I'll see you tomorrow.